at example 4, we're going to find f times function f. So that's just f of x times f of x. That will be the square root of 3x times the square root of 3x, which equals 3x. Now, while our answer, the domain, you could be all real numbers, you do have to take into consideration the original two functions. So the domain is not all real numbers, because if you're undefined to begin with, then you can't have a solution. So the domain still has to be everywhere where 3x is greater than or equal to 0. So where x is greater than or equal to 0. So this domain is going to go from 0, including 0, all the way to infinity. Looking at C, we have f of x divided by g of x, which looks like this. And then let's simplify this radical in the denominator. So it's the square root of 3x over, and this would be, when we factored out the x, we're left with x squared subtract 1. Now the square root of 3x over the square root of 3x times 1 over the square root of x plus 1, x minus 1, if I factor that. So this is going to cancel, and our final answer is this, 1 over the square root of x plus 1, x minus 1. The domain is all real numbers, except for we have a problem here because I cannot have the denominator be 0, and I cannot have a negative underneath the square root. And you could rationalize this. I'm going to just leave it as is for now. And let's focus on the domain. All right, so as far as the domain goes, and I'm kind of out of room. Hold on. So I'm not too concerned about rationalizing the denominator. You can actually leave it just like that. But what I am concerned about is the domain. So the domain of f divided by g, or f of x divided by g of x. We have to look at the domain of the numerator, the domain of the denominator, and then where those domains overlap together. So what would the domain of the numerator be? We've got the square root of 3x. Well, we know that 3x would have to be greater than or equal to 0, which means x would have to be greater than or divide by 3, and you get x is greater than or equal to 0. So here's 0, and if I want to do the domain of f, so here's f, on this number line, it's going to be 0, and it's everything to the right. All right, so now what I want to do is find the domain of the denominator. Here's the denominator, and I know that the denominator can't be 0, and it can't be a negative underneath that radical. So what I would do first is find the critical values. So if I have x plus 1, you just set that factor equal to 0. Here's the first factor. And then x subtract 1 and set that factor equal to 0. All right, so x is equal to -1 and x is equal to +1. So here's -1, and I know that I cannot use -1 because that'll give me a 0 in the denominator. And I know that I cannot use +1 because that will also give me a 0 in the denominator. Now, like we did before, I want you guys to think about areas. So we have all of these numbers over here. So I might want to try maybe -2. And then in the middle, I might want to try 0. And then over here, I might want to try +2. And what I'm going to do is plug it into this denominator. to see if it's positive or negative. And I only want positives because I can't have a negative under the square root. So let's start with -2. I would have -2 plus 1 times -2 subtract 1. And -2 plus 1 is -1 times -3, and two negatives give me a positive. So all of the numbers to the left in that number line are going to be positive. In this middle part, when I plug in 0, I would get 0 plus 1. Again, I'm plugging it into this x plus 1 times x minus 1. I would get 0 plus 1 is 1, and 0 minus 1 is -1, and that is going to come out negative, which means I cannot use any numbers in that area there from -1 to 1. And then try 2. So this would be 2 plus 1 times 2 subtract 1. That gives me 3 times positive 1. Almost messed up there. And that gives me 3, which is positive. So all the numbers to the right of 1 are good. Now, I have to pick numbers that overlap. So for the denominator, even though all those numbers over here are defined, it doesn't overlap with the numerator. So I would start at 1, and 1 is no good, but everything in this direction would work. And so you can see, where do the numerator and the denominator overlap? It's everywhere from 1, not including 1, to infinity. So what is the domain of f of x divided by g of x? The final domain is going to be 0 to infinity. Not 0, come on, 1 to infinity, not including the 1. 1 to infinity. And that's your domain. So now we're going to look at the domain of a composition function. Now the other functions, when you add, subtract, multiply, divide, you look at the domain of both functions and the domain of the answer. The composition function is a little bit different. You don't have to look at the domain of both functions. You only have to look at the domain of what you input, which is right here, and the domain of what the output is. We don't care about the domain of f of x because we're not really using the domain of f of x. G of x would be the new domain. So let's look at example 5, and we will go ahead and take the composition function, and then we will look at the domain. So we have f of g of x. So this, I like to call it fog, is f of g of x. So we start with g of x, which is x squared subtract 5. That's the new domain of function f. So we plug that into function f, and we get the square root of x squared subtract 5. Now that wasn't too bad, but now what we're going to do is figure out what in the world is the domain of this answer. So when we're looking for the domain, we only have to find the domain of what we input and the domain of what the output is, and that will be our domain. So the input has to be greater than or equal to 0, and so x squared subtract 5, and the reason why is because the output has it underneath a square root symbol. So just add the 5, so x squared is greater than or equal to 5, and then use square root both sides. Don't forget, plus or minus, and x is greater than or equal to plus or minus the square root of 5. So the square root of 5 is what gives me a 0 underneath that square root symbol. And 0 is okay because we're not on the bottom of a fraction. but I can only have under here, only have positive numbers. If I have negative numbers, it's undefined. So here's my number line. I'm going to try some critical values. So actually my critical values are -5 and positive √5. I'm going to try, so the square root of 4 is 2. So I could say, I could try -3. I could try 0, and I could try +3. So I'm going to take those, plug them into here, looking for positive answers. So if I take -3 and I square it and I subtract 5, I'm going to get a +4. So that is good. If I take 0 and square it and subtract 5, I'm going to get a negative answer. So everything in between there is no good. If I take 3 and square it, I get 9, subtract 5, which is +4. So I am good with all of the values going in that direction and all of the values in that direction. So therefore, my domain of f of g of x, here I am, and I know this has been kind of messy, but my domain is going to go from -∞ to -√5 union, and then I'm going to pick up at +√5, and I'm going to go to infinity. And you know what? These need to be brackets because the √5 was just fine. It just gives me 0. So brackets on there, and I'm going to stop the video and try to rewrite that because it looks super messy. Next problem is g of f of x. So g of f of x, or golf, kind of like golf without the L. All right, golf, g of f of x. So you're going to start with f of x. F of x is the square root of x. And you're going to plug that into function g. So function g is x squared subtract 5. So that's the square root of x squared subtract 5. And I'll end up with x subtract 5. Now, the composition function's domain is I have to look at the domain of my input and the domain of my output. Now, my output, x, has to be a positive number here because my input, it's underneath the radical, and I can't have a negative underneath that radical. So I am going to go ahead and take x, I'm going to take x has to be greater than or equal to 0. So that's this right here. And so my domain is going to go from 0 to infinity. So the next thing we're going to do is decompose a function. If you have f of g of x, so to decompose a function, you're going to break apart the function and figure out what is f of x and what is g of x in that composition function. There is more than one correct answer many times, so it's not a unique solution. But if I tell you that here is the function and it's been composed of f of g of x, what is f of x and what is g of x? What I like to do is, you notice how g of x is on the inside of the function. I like to take these parts that are on the inside of the function and let them represent g of x. So g of x is going to be x subtract 1. Here we are, g of x, x subtract 1. Now, f of x, what I can do with f of x is I can replace these insides with x. So f of x is going to be x squared plus 2x subtract 7. And when I find f of g of x, I would take g of x, I would plug them into where I see x, and that would give me my composition function. So basically, I'm taking a composition and breaking it up into pieces. So an implicitly defined function is where we take a function and basically solve for y. It would be a function that we could put into our graphing calculator. So this happens to be a circle, but I can't graph a circle in my graphing calculator. So what I'm going to do is just solve for y. So in order to solve for y, I would have 3x squared is equal to y squared plus 15. And I want to get rid of that 15. So I would subtract 15 over here. And then I have y squared equals 3x squared subtract 15. And I want to solve for y, so I'm going to square root both sides and make sure that you remember the plus or minus. So the implicitly defined function is going to be y equals the positive part of 3x squared subtract 15, taking the square root of it, and y equals the negative part of the square root of 3x squared subtract 15. If you were to graph both of these pieces in your graphing calculator at the same time, then you would see the circle. So that is implicitly defined function. While a relation is simply a set of ordered pairs, that's supposed to be yellow, a function is a special type of relation. So while the circle is not a function, I was able to break it apart into two functions. Implicitly defined function. Looking at example 8, x squared plus y squared equals 9 is a circle. And it's a circle that has a radius of 3 and whose center is at 0, 0. So if I were to graph this, we get this circle. And what I'm going to do is break it up into two pieces that are functions. And so we're going to get a piece of the circle here, and then we're going to break it up into a piece of the circle there. And both of those would pass the vertical line test, being functions. So looking at this, I'm going to solve for y squared. I'm going to solve for y. So I'll start with y squared equals 9 subtract x squared. And then I'll square root both sides. Don't forget the plus or minus. And y is equal to the positive part, square root of 9 subtract x squared, and the negative part of the 9 subtract x squared. And so you can graph that on your calculator. If you graph both pieces, you'll see this circle. But if you're looking at each piece separately, we have an implicitly defined function. Challenge on the U-try is you've got g of f of x, and you are going to tell me what is f of x, and f of x is the inside of the function. So think of this as the inside of the function. And then you're going to tell me what g of x is equal to. And if you were to combine those into g of f of x, you would get this. Sometimes they'll call this h of x. So see if you can do this problem two different ways, because there are two ways that I can think of, maybe even three ways that you could tell me what f of x and g of x are. Make sure you do the reflection. Have a great day.